Gravity built every galaxy you've ever seen. It holds you to the floor right now. It bends light across billions of light years and dictates the fate of the cosmos. Yet, after a century of effort, physicists still can't make gravity fit with the quantum framework that describes everything else. Electromagnetism, the strong force, and the weak force all obey quantum field theory. They live inside the same mathematical structure. Gravity refuses, not because it's too weak or we lack a bigger accelerator, but because, as Einstein revealed, gravity is not a force living inside spacetime. Gravity is spacetime geometry. This single fact creates a structural incompatibility that's one of the deepest unsolved problems in science. Today we'll break it down. Why the other forces quantize beautifully, why gravity doesn't, the crises at black holes and the Big Bang, and Hawking radiation. We'll incorporate fresh perspectives on time-dilated evaporation, blue-shifted photons, and the firewall-like effects near horizons. The three quantum forces are gauge theories with symmetries. Photons mediate electromagnetism with incredible precision. QED predicts the electron's magnetic moment to better than 1 part in a trillion. Gluons bind quarks with asymptotic freedom. The weak force unifies with electromagnetism via the Higgs at high energies. All operate on a fixed space-time background. Particles are excitations of fields. Virtual particles mediate forces. Renormalization tames infinities. Space-time is the inert stage. Einstein's general relativity flips this. Mass energy curves space-time. Objects follow geodesics, the straightest paths in curved geometry. Matter tells space-time how to curve. Curved space-time tells matter how to move. Newton's instantaneous force becomes geometry. Confirmed by light bending in the 1919 eclipse, GPS time dilation, and LIGO gravitational waves. GR is background independent. Space-time is the dynamic field. Trying to quantize it means quantizing the background itself, losing the fixed reference for defining particles. Diffeomorphism invariance clashes with QFT gauge symmetries. Perturbative gravitons self-interact because they carry energy. Higher-order diagrams explode with infinities that renormalization can't absorb. Gravity's non-linearity and universality doom the standard approach. Maybe it's really this simple. Gravity is not a force. Instead, it is space-time geometry. This isn't a flaw in GR, it's why it breaks at Planck lengths. Where quantum effects dominate, the smooth geometry of GR meets the granular reality of the quantum. Black holes expose this crisis. In general relativity, the event horizon is a one-way boundary. Nothing escapes, not even light. It's the point of no return. For a static, eternal black hole, the horizon is smooth. A free-falling observer would notice nothing special as they crossed. But real black holes evaporate via Hawking radiation. Quantum vacuum fluctuations near the horizon create particle-antiparticle pairs. One falls in, the other escapes as radiation. The black hole loses mass. This changes everything we thought we knew about horizons. We must re-examine GR for dynamic horizons due to massive time-dilated evaporation. Hawking photons carry mass-equivalent energy away, shrinking the hole down to Planck scales, and possibly trans-Planckian distances. The experience of an observer falling in changes dramatically. For inertial observers falling in, cold Hawking photons appear blue-shifted to quark-probing gamma rays. These interactions are intense. This suggests the horizon isn't uneventful. Quantum effects might create a firewall of high-energy particles, challenging the equivalence principle. The infalling observer's experience differs dramatically from the distant one due to extreme time dilation and blue shifting. Hawking's calculation implies information loss. Radiation seems thermal and random, violating the quantum rule that information is never lost. This violates quantum unitarity. If information is lost, the foundations of quantum mechanics crumble. This is the information loss paradox. But there is a resolution. As one perspective suggests, the information loss paradox evaporates as nothing ever crosses the event horizon. The infalling observer is entangled with the outgoing Hawking photons. Information is preserved through this quantum connection. Don Page predicted that the entanglement entropy would rise and then fall. This Page curve is the signature of information preservation. Radiation purifies as the whole evaporates. Recent holographic models like ADS/CFT recover the Page curve, suggesting gravity is subtle. Dynamic horizons tie in. Evaporation makes the horizon fuzzy at quantum scales. Entanglement preserves information outside the hole. Blue-shifted photons and high-energy interactions near the horizon could facilitate this transfer, resolving the paradox without violating GR. Similar singularities plagued the Big Bang. General relativity predicts infinite density and curvature at the very beginning of time. Quantum gravity is needed at the Planck time, a fraction of a second after the start. Inflation helps, but the need for a theory remains. GR is an effective theory, brilliant in its domain, like fluid mechanics for water, but it hides the underlying molecules. It is incomplete at the extremes. Quantum gravity must be background independent, non-linear, and reconcile geometry with quantum fluctuations. Progress is being made through ADS/CFT duality, black hole microstates, and new page curve calculations. We are getting closer. Future gravitational wave detectors and CMB polarization maps will search for the imprints of quantum gravity on the cosmos. Even tabletop experiments might reveal how gravity interacts with quantum systems. The quest is becoming practical. Dynamic horizons and transplanckian effects could mean horizons preserve information and smooth the quantum classical transition. Gravity as space-time geometry isn't the problem. It's the key to a deeper, unified reality. The universe's deepest secrets lie here. Physics advances by confronting these tensions. It's about understanding if space-time emerges, if time begins, and our place in the cosmos. The universe's deepest secrets lie at this intersection. Physics isn't just about equations, it's about the very fabric of our existence. Thank you for watching Frequency XO Productions. We hope this deep dive sparked your curiosity. If you enjoyed this exploration of the cosmos, please subscribe for more deep dives into the fabric of reality. Thank you for watching Frequency XO Productions, and remember, never give up on yourself. The universe is vast and so is your potential. Stay curious, keep searching, and find your own frequency.